I'm Kevin. Welcome to my cave. In the episodes of Transistor 101 leading up to this point, we've managed to design quite a few building blocks. We've looked at current sources and current amplifiers, including both single-ended emitter followers and push-pull pairs. We've seen how we can boost current gain with Darlington and Cycli pairs. We've built voltage amplifiers with the common emitter configuration, and we've learned how to increase their gain and stabilize their biasing by bypassing the emitter resistor with a capacitor. And we've built saturated switches and examined the limits to how much current they can deliver. But we're starting to get a little stuck on our mental model of a transistor. Our picture of transistor person tirelessly adjusting a variable resistance to keep the collector current proportional to the base current has begun to break down. We're finding that our diode drop isn't a constant 600 millivolts at all, and that the gain we're getting when we try to design high-gain amplifiers is less than we predict. Even worse, the amplifiers themselves don't have a linear response. We need to get to the bottom of what's going on. It turns out that we want a different model of transistors, as voltage-controlled devices rather than current-controlled ones. In order to study that model, I'm going to want to look at both diodes and transistors, and measure the current through them as I vary the voltage across them. With a diode, there are only two terminals, so I'm just talking about forward or reverse current. With a transistor, I want to see collector current, or emitter current, it's basically the same thing, as I vary the base voltage. But I don't want to measure lots of voltages and currents manually. For one thing, I'm lazy. For another thing, it's not great for the device. A small overvoltage could yield a massive overcurrent and blow the device. So I think I need to hack together a test rig. The tester needs to apply either a known voltage and measure the current, or else regulate the current to a known level and measure the voltage that produces it. And it needs to record the measurements. My digital scope can do that, of course. There are a few more challenges here. My scope can't measure a current directly, so I have to measure the voltage drop across a resistor. That voltage and the anode, cathode, or base emitter voltage need to be relative to ground. I don't have differential probes for my scope. The currents I want to measure vary from nanoamps to milliamps, so I have power constraints at one end and noise constraints at the other. I'd like to get to at least a 10,000 to 1 ratio. And at the high end, I have to limit the current to avoid letting out any magic smoke. The circuit has to remove the drive voltage promptly. With what we know about op-amp circuits, I think we have the tools to design this tester. Let's sharpen our pencils and get to work. Here's the idea. I'm going to have a device under test and drive its input with a circuit that generates a varying voltage between base and emitter. I'm going to want to measure the current at the emitter somehow. I'll buffer and amplify the drive voltage. I'll set my oscilloscope in XY mode to display the drive voltage on one axis and the current on the other. We will want to have a preset upper limit on the current and reset the variable voltage generation when we hit it. We can quit resetting when we hit a preset lower limit to allow the voltage and current to rise again. We already know a circuit that can make that happen. It's the Schmidt trigger that we saw in an earlier episode. Ideally, I'd like the scope ground to be the emitter of the transistor. But I also want the scope ground to be the power supply ground. And I can't just ground the emitter. What would limit or sense the current? So I set about in my notebook sketching a design with differential amplifiers, which I haven't discussed yet, to deliver the voltages to the scope. In the morning, it came to me in the shower. I can't make the emitter a ground, but I can make it a virtual ground. Let's take a closer look at the current sensing circuit. We'll have our device under test and apply a voltage to the base or the anode. We'll hook up the emitter or cathode to the minus input of an op-amp, and we'll ground the plus input. Remember that an op-amp holds its inputs at equal voltages. That means that the minus input will also be at ground. We'll need a feedback path, of course. That can be a simple resistor. Next, remember that the inputs of an op-amp draw nearly zero current. That means that the current flowing out of the device under test will equal the current in the feedback resistor. So Ohm's law tells us what the output voltage has to be. It'll be proportional to the current through the device. It'll have the opposite sign, but I don't really care. I can put in an inverter, or simply tell my oscilloscope to invert the input. And both the base voltage and the output voltage are relative to ground, which is exactly what we wanted. In the initial design, I made the current measuring circuit look like this. For R4, I put a collection of resistors side by side on the breadboard, with values 1K, 10K, 100K, 1 meg, and 10 meg. Those let me select the scale for reading out the current as a voltage. If I assume a 10-volt full-scale output signal, I get full-scale ranges from 1 microamp to 10 milliamps. I've shown the bypass capacitors on both power rails. We're going to see that the current is extremely low for most of the cycle, so I want to make sure I have an accurate virtual ground. I added an offset trim to the op-amp to make it as accurate as possible. I got the circuit right out of the TL071 datasheet. Because the output of the current sense circuit is a negative voltage for a positive current through the device, I put it through a unity gain inverter before sending it to the scope. The generator for the variable voltage is the integrator that we saw in a recent episode. I wanted to use quite a small capacitor so that it will discharge quickly at the end of a cycle. With the component values shown here, the voltage should ramp up from 0 to a diode drop in a millisecond or so. The switch I'm using is a JFET. I'm not planning to cover those in detail for a while. I'll just give you a cookbook approach for including one in an integrator. First off, the voltage at the source and drain of the JFET must be above ground. You can get away with as much as a diode drop below, but it's poor practice to push things. Here, the source terminal is at virtual ground, and the drain is positive because we're integrating a negative voltage, so there should be no worries. The gate is a voltage-controlled terminal. If it's a negative voltage below the threshold of the transistor, then the switch is off and the integrator integrates. JFET threshold isn't a well-controlled parameter. The datasheet for the J112 that I'm using says that it should be between -1 and -5 volts. Throwing -12 at it will surely turn it off. If the voltage at the gate is near ground, the JFET conducts and the capacitor discharges, resetting the integrator. If we can turn a reset signal on and off at the right times, we can generate a ramp wave. Incidentally, there's a ramp circuit like this at the core of a lot of voltage-controlled oscillators. Put a pin in that. We'll likely come back to it in a musical context. The ramp voltage goes to the oscilloscope through a non-inverting op-amp buffer. Because the voltage is so small, at most a diode drop, I use an amplifier with a gain of 10. Nothing new here. The only remaining block is the generator for the reset signal. It might look a little intimidating, but it's just a Schmidt trigger. We had a whole episode discussing them. The difference from the Schmidt trigger that we saw earlier is that instead of generating a logic level output, we are generating the ground and -12 volts that our ramp generator needs. That's done by tying the pull-up R11 to ground rather than logic high, and the pin on the chip that's labeled ground to the negative rail instead. The analysis works the same way as before, by making the currents at the plus input of the op-amp sum to 0. I'll drop a Python script on the project GitHub and link it down in the doobly-doo. Because the input and output voltages are both negative, I kept confusing myself with the calculation. I wound up making a table to make sure I had all the signs right. When the device current is rising, the voltage on pin 3 is falling. The voltage on pin 2 will be the lower trigger point. The the pin 3 voltage will be greater, that is, less negative, than the trigger point. The comparator output will be forced to negative 12 volts. The only components carrying DC current are the resistors. By now, we can analyze the network on autopilot. And negative 12 volts on the reset line means that the integrator should integrate. When the device current is falling, the voltage on pin 3 is rising. The voltage on pin 2 will be the upper trigger point. The pin 3 voltage will be less, that is, more negative, than the trigger point. The comparator output will be an open circuit. We can still analyze by working through the resistor currents. Once again, I'll do it on autopilot. Finally, we can compute the voltage on the reset line. Less than 1/10 of a volt. That's close enough to the ground that the JFET will be in full conduction. The integrator will reset. That completes our circuit. I'm confident enough that I'm not going to bother to simulate it. I think it'll be quicker just to take this first version to the breadboard. And I think that's where I'm going to leave it for this time, because otherwise this is going to be quite a long video. We've completed a design for our test rig, so this is a good stopping point before we start to build and test. I'm still learning what works and what doesn't, so let me know in the comments whether you'd rather see a project like this be presented in fewer, longer videos or more shorter ones. Next time, as I said, I'll get on to building and testing this setup, so stay tuned for that. In the meantime, stay safe, stay healthy, stay curious, and take care of one another. Bye!